Okay, welcome to part 3, C++, week 10. We're talking about pointers and references in this PowerPoint. There's 72 slides, so hopefully we can get through it. It's a lot of information. We'll go slow, but once it clicks, it gets easier. So we're going to talk about all of these things. We're going to talk about what a pointer is, how to declare a pointer or how to make one, how to store addresses in pointers, so how to actually point them to something, how to dereference a pointer, which basically means how we can read information from it, a dynamic memory with dynamically creating memory during your program at runtime. And then pointer arithmetic. We can actually perform mathematical operations on pointers, which is something that they have as an advantage over references. We're going to talk about pass by reference with pointers and consts and pointers, just like we talked about consts and references last week. We're going to talk about using pointers and passing them to functions, and then some of the most popular pitfalls that happen with pointers when you're using them. What are the common errors? We'll talk about what a reference is and references versus pointers, when to use a reference and when to use a pointer, the similarities and differences between them. We'll talk about passing references to functions. That was sort of covered last week. So if you want to watch the video from last week in week 9, then go ahead and watch that. Consts and references was also covered in that video. And then reference variables in range-based for loops. All of those things were covered last week, so I'm not going to get into them too much this week. We're going to focus more on pointers, but we will talk about references a little bit at the beginning here to kind of get us, debriefed on what we're covering. And then at the very end, I'll just talk about some of the similarities and differences between raw pointers and smart pointers. Cool. So you may have heard some of the horror stories from programmers about how difficult pointers can be and what they can cause when they're used improperly. A lot of programming languages don't use pointers because they cause so many issues. Now with C++, it gives us so much more power over our machine than we can ever achieve with languages like Java or Python. Not to knock on Java or Python, but it just comes down to the way the languages are created and the domains that they're typically used on. And C++ specifically is used to extensively develop Windows, Mac, embedded systems, system software, that kind of thing. And with that means we need access to, allocate memory, dynamic memory on our machine. So tons of power there. With that power, like I said earlier, comes great responsibility. Responsibility on how to understand and how to use and how to release the memory efficiently and correctly. So we want to make sure that we're using the pointers for those use cases when it makes sense. A pointer, if you think about it, is a variable, okay? That's all it is. It's a variable. So don't let it confuse you. A pointer is a variable. Now, when we talked about references, remember, we were talking about using the ampersand symbol, okay? And the ampersand symbol, let's see if I can draw here, if I can annotate. The ampersand symbol is this, right? And we put that in front of a variable, and we use that to reference, that address or that memory address, that memory location of a variable. Pointers are very, very similar to what we talked about last week with reference variables. Everything we learn in this section is using C++ pointers, okay? Not like raw pointers. We're not talking about smart pointers here. We're only talking about C++ raw pointers, okay? There's a ton of code out there that uses raw pointers, so it's really important to understand them completely. C++ also has smart pointers, but they eliminate many of the safety problems that raw pointers still have. While smart pointers are used more often with object orientation, their topic, which we will talk about if we have time in this course, in the future. But right now, an introduction to raw pointers only is going to be what we're covering, okay? Cool. Good to know that about Java there. So in Java, You cannot do pointer arithmetic, and you can't dereference a specific memory address or increment a pointer. So that is why C++, there is so much power there with pointers. Okay, so before we get into all this stuff about pointers, let's kind of have a little review on what a reference is, okay? A reference, in short, is an alias for a variable. So if we have a variable num and num equals 10, and then we make a reference to num, it's an alias for what num is holding, okay? For that address in memory for what num is holding. It must be initialized to a variable when it's declared, okay? You can't leave it null. And once it's initialized, it can't be made to reference a different variable. You can't change it. So once a reference is made an alias to a variable, it stays like that. Very useful to use as function parameters because remember, like last week, you don't have to copy a large data structure like a vector. You can just pass the original reference to the data structure, and then it's actually changing the data structure itself. It's not making a copy, then passing the copy back, then replacing the original with the copy. It's just doing it all in one shot, and it saves you a ton of overhead with memory and machine power. That's not the correct technical term, but it saves. It's more efficient. It might be helpful to think of a reference as a constant pointer that is automatically dereferenced. I'll mention that at the end again, but basically, whenever we use a reference, we're actually using the variable it refers to. Okay, you're not changing a copy of it. You're actually changing the original variable it's referring to. So when you first start out in C++, it can be a bit confusing, but references are just the variable they refer to. Okay, hopefully that makes sense. So here is an example of a reference in a range-based for loop. Okay, so we talked about for loops, and range-based for loops are kind of like for each item in a collection, it will loop through it that many times. So it automatically knows that the size of this specific vector, Larry, Mo, and Curly, are 3 strings. Okay, so we can see our for loop here, our for range-based for loop. We're using auto, so it will find out that it's a string. And then we call str, we make this variable whatever name we want it in the vector stooges. And we change str and we set it to funny. Okay, we assign the value of funny to each string in stooges. So what's happening here is that each iteration of stooges, we're assigning the word funny to each element in the loop. Now, the problem here is later on when I go to print it out, so here I have the same range-based for loop that's going through stooges, and I see out it to the console. What's happening when we print the string is it's still going to print Larry, Mo, and Curly. You can try this right now in your IDE, but the problem was what happened was the first loop here, it's changing a copy of each item in the vector as we loop through it. And then down here, it's going to print the original. So it only changes the copy. It doesn't actually update it. So this is where references come handy. Part of the code that's different. So instead of just calling it str, we do ampersand str. And now we're referencing each of the string objects, the original string objects, and it's an alias for those objects. Okay, so we're assigning funny to str. We're actually changing the original vector element to funny. And then if we add, obviously, a const qualifier, which you'll see on the next slide, it makes it read only, which we kind of experimented with last week. But we can see here as we see out to the console, it actually changes the original string objects. Okay, so here if we use the const keyword and do ampersand str, then when we set it to funny, when we try to assign a value to it, because it's a const, it won't let us change it. It's a read-only variable, right? So we're preventing any change to the data in the vector because the compiler has marked it as read-only. So we'll get a compiler error if we try to do this. By using a reference, we're not incurring any cost of copying each vector into each loop iteration. So it's actually a lot more efficient in your code, especially with larger data structures like vectors. Okay, and then here, this won't give us a console error because Larry, Moe, and Curly, okay, they're strings. We have a const, but we're not changing it. We're just printing it out to the screen, okay? So then it will print out Larry, Moe, and Curly. That's perfect. For a display function, we want it to be a const, so it won't actually allow us, if we accidentally or on purpose, try to assign a value to it, okay? So unless you have a specific reason to copy your elements in a range-based for loop, you should use reference variables, okay, to make your code more efficient. And if you're not going to modify a collection, so if we're not modifying, you're just printing it out, you should make the reference a const. Okay, so just a couple simple rules there. Because copying vectors is expensive in terms of memory, okay? All right. So I have a little quick example here in CodeLite that I'll show you just to give a little bit more hands-on with references. Okay, so I'll just bring this over here. So I'm in week 10 references. Now, this code, I haven't actually put it on Blackboard. It's a lot of code and there's a lot of stuff that could be confusing. But if you do want to follow along or you find an example helpful, then feel free to pause the video or, just write this code down in your IDE and test it for yourself because I think this stuff can be really, really helpful. So we'll go through it a little bit at a time and just kind of break this down, okay? So here I've got a variable called num, all right? And I've set it or initialized it to 100, okay? Then I've got a variable that's a reference variable because I put the ampersand symbol in front of it. And I referenced it to num, okay? We can't reference it to nothing. Remember, it can't be null. So we initialized it to num. So let's say here, for example, I'm going to try my hand at drawing this. Okay. That num, it has a value. Whoops. I don't like the color yellow. I don't think it shows up very well. Red. I'm just going to move that. So let's say num has a value of 100, right? But let's say in memory, okay, the address is going to be some hexadecimal address. It's going to be like 6EX F, oops, FF, whatever. It's going to look like that. So that's the address in memory. Now, when we make a reference to num, what reference is going to do, okay, with the ampersand symbol, is it's going to be stored to this value, 6EXFFD4, right? Now, if we just call ref itself, then it will print the value that the reference is pointing to, okay? And I can't use the word pointing to, that it's referencing, okay? So let's take a look at this. Let's run this. So we've got 100, and then we set a reference to the value num that's holding 100. So we'll print num, we should get 100 because that's what's expected. And if we print ref, we should get 100 because it's referencing num. Okay. Let's take a look here. Control F5. And sure enough, I bring this over and I zoom in. We've got 100 and we've got 100. Okay, now while I've got this open, I might as well do this all at the same time. So coming down to line 15, we set num to 200. Okay, so we've updated num, we've assigned it to a new number. And then we print out a bunch of dashes. So that's what's happening here. And then when we see out num and ref again, well, num obviously was updated because we changed it. But look at the reference variable also is updated because it's referencing the original value of what it's referencing. Now, if we change ref to 300, okay, instead of num, we're changing the reference to 300. Well, when we print num and ref again, look, they're both changed to 300. They're identical. They're the same. Okay, so now with strings, let's try it with strings. We print out a bunch of dashes again, and we make a vector of strings called stooges, str equals funny. Okay, str is a copy of each vector element here. Okay, this is a copy. So when we set it to a copy and we try to print it later on, look, there is no change. It still printed out Larry, Moe, and Curly because it changed the copy. So then when we loop through here, out to the console, it doesn't change. Now I make my reference to the vector stooges a reference to each vector element with the ampersand symbol, and then I assign the value funny to it. And look, it changed the originals down here when it loops through, and I made it a const because it's a read only. And now the actual vector elements have changed. Does that make sense? Hopefully that makes sense. That's references, okay? So that's a quick little overview of references, and then we're going to talk about pointers basically for the rest of the day. Cool? Any questions? Nope. Good. Okay, that's great. Everyone's on the same page so far. Okay. Well, let's talk about what a pointer is. Okay. So a pointer is very similar to a reference. Try not to confuse them now. It's a different thing. It's a variable. Okay, pointer is a variable, but instead of its value being like 100, like a number, its value is an address in memory. Okay, it's that hexadecimal address. Okay, it's a memory location that's bound to a variable. It points to a variable or a function. Okay, now what can be at that address? A variable or a function. Okay, it points to if x is an integer variable and its value is 10, okay, like our example, then I can declare a pointer that points to, must know the data type, okay? So if we want to actually dereference it, we need to know the data type that that pointer is pointing to. So when you create a pointer, you actually create the type of variable that it's going to be pointing to. So if I have x, which is an integer of 10, when I create a pointer to x, I need to make an int pointer, okay? It's not just like one size fits all. Okay, so why do we use pointers? Can't I just use a variable or a function itself? Yes, you can, and you should when it makes sense, but not always, okay? We want to be able to sometimes access data from within functions because of scope, right? We have, global variables or local variables, and sometimes copying a variable from one function to another function can be very expensive in terms of memory. So it makes sense to just modify the original code or the original values itself instead of making a copy of everything, okay? So inside functions, pointers can be used to access data that are defined outside the function. So you don't actually need to pass anything in. Those variables may not be in scope, so you can't access them by their name. So pointers can actually be used to operate on arrays very efficiently, much like what was pointed out earlier with using subscript syntax. There's a relationship between pointers and arrays that we'll talk about in a little bit. And it allows us to access data at runtime. It doesn't have to have a variable within it, so we can use a pointer. Okay, so this might make sense to do if we are using or coding stuff for embedded systems, drivers, device software. It uses things like memory addresses often in those types of programs. Okay, we can allocate memory dynamically on the heap. For the heap, this memory never gets a variable name, and the only way to get it is via a pointer. Okay, so the only way to access that data that you allocated on the heap is through a pointer to that data. So with object-oriented pointers, pointers are how polymorphism works with object-oriented programming. We'll talk about polymorphism again if we have time. It's a more advanced topic, and we'll cover it briefly. But we have to understand pointers first before we get into that. And we can access specific addresses in memory, which is really useful, like I said, in embedded systems, drivers, system applications, all of that stuff. Cool. So that's why we would use pointers. So how do we declare a pointer? How do we make one? Well, you have to have the variable type. Like I said, it has to know the type of data it's pointing to, and then the pointer name. Notice the key symbol here is the asterisk. Okay, that's how we make a pointer. So if we want to make a pointer that points to an int, we call it whatever our pointer name is. So in this case, it's int pointer with an asterisk in front of it. Now notice here for double, the asterisk is on double. Okay, you can do either. The way we do these declarations is from right to left. So int pointer points to an integer. So Double pointer points to a double. Character pointer points to a character. String pointer points to a string. So read right to left. Okay. Now, notice the asterisk can be on either side. It doesn't matter. It's equivalent styles. Some people have a preference for one. Some people have a preference for the other. It's up to you what you decide. Okay. And something very important to notice here is if we don't initialize our variables, the pointer will contain garbage data. It's a variable, right? So if we don't initialize it, it's going to just point to a random address. It will have random garbage data, and who knows where that's pointing to machine. It could be point of information of memory, and when we try to modify it, it could corrupt our system or something. Okay, so initializing it is very important. Usually, what you want to do is initialize it to nowhere. We want it to point to nothing, because if we leave it not null, if we don't initialize it, it will point to something, and we don't know what it's pointing to. It could be pointing to some really important system driver on your machine, and then later on, when you try to update that address in memory to equal 100, and say it was supposed to be a 0 or a 1 in your registry, you could really mess up something quite important on your machine. So we want to always initialize them to point to nowhere, to null, okay? Because then that way we know we're not messing with something we don't want to be messing with. We use the same list initialization syntax that we've been learning about with the curly braces. And just keep in mind, null pointer means it points to nowhere. It's better than pointing to somewhere random. So down here, you want to put in null pointer. That would be wrong. So these are correct. Okay, good. All right, so declaring a pointer. When we initialize our pointer, we want to make sure it points to nowhere. We want to always initialize them. Remember, uninitialized pointers contain garbage data and can point anywhere. And then initializing to 0 or null pointer, which is something that came out in C++11, represents address 0, okay? It implies that the pointer is pointing nowhere. And if you don't initialize a pointer to point somewhere, then you should initialize it to null pointer to make it null. Okay, so those are just a couple of notes on declaring pointers. So now we know how to actually declare them. All right, now let's talk about accessing the pointer address. So we've declared it. Well, we use the address operator, and that's the same ampersand symbol that we were talking about earlier today with references. So, for example, the address operator is that hex code for location in memory for what holds the value of num, right? In this example, it's a variable that stores a unique address, and it evaluates to the address of its operand. The operand cannot be a constant or expression that evaluates to temp values. So here we've got an int num that's initialized to 10. The value of num is num, okay, that'll print 10. The size of num is, and we use the size of function. So we've talked about that before. It's the CMath library. And that, depending on your machine, could be 4. On my machine, it could be 8. On your machine, it could be 4. It just depends how many bytes your machine allocates to an integer. So that could print 4 or 8. And then the address of num, and here's where we use that address operator, okay? And this is where it prints that hexadecimal value, okay? So how do we access a pointer? Okay, well, the address operator. So here we've got a pointer called p, and it's pointing to an int, okay? Now we haven't initialized it here, so it's going to be containing some garbage value. So the value of p is, and then we print p just itself, and it's got some garbage value. Now, the address of p is, and here we can see it's the ampersand sign and then p, and look, it's the same address except for 18 instead of 60. So the address of what the pointer is different than the value of what it is. So the value of it points to an address, and then the address of it is where it is the size of function. And then see, it's 4 on my machine. It might be 8. And then here we set it to null pointer. So we're setting it to point to nowhere. And then when we get the value of p again, it's 0. Okay, so that's how we can access pointer addresses. When we assign null pointer to p, since p is a variable, we can change its value. This is really important because when we talked about references earlier, you can't change a reference once it's initialized. Remember? Here we can change what a pointer is pointing to, but with a reference, you can't change it. Okay, so this is really important to remember, and it's a huge upside to using pointers over references if you need to be able to change it. Okay, so let's get into accessing pointer addresses. The size of, okay, pointer variable. Let's talk about that a little bit. So don't confuse the size of a pointer and the size of what it points to. All right, so remember, you have the address of what the pointer actually is, and that has its own size. And then you have the value of what the pointer points to, which is another address. But it's a different address than where the pointer sits. It's the address of what it's pointing to and where it sits and its size. Okay, so you have two things going on here. Don't get confused here. It's not too difficult. But basically, all pointers in a program have the same size. So they may be pointing to an int or a double or a vector, which is a large data type, or just a char, which is a small data type. But all pointers have the same size. So if we print this out, right, we'll size p1 if I do the size of function less than, because one's an int and one's a vector. What do you guys think? If I do the size of function on p1 and the size of on p4, will they be the same or will they be different? Write your answers down below and tell me what you think. You think they'll be different? Okay, well, we have some people saying they're different. Actually, if you said that they will all be a size of 4, then you're right. Okay, so the size of pointer variable and the size of what a pointer variable points to are different. Make sure you understand this. Okay, so I see that in chat you have the example of all houses have a mailbox, but not all houses are the same size. Okay, but all the mailboxes are the same size, right? Which is the pointer itself. But then what the pointer points to, which is the address for the houses can be a different size, right? So imagine you live in the country and you have those green emergency numbers at the end of your driveway, right? And there's, the city gives out mailboxes and they have to be they're all uniform mailboxes. They're all the pointers. They all have the address of the house that they belong to. Okay, all the mailboxes at the end of the road, you have mailbox 1, mailbox 2, mailbox 3, mailbox 4. And let's say mailbox 1 is just a tiny house. It's just an int, okay? And its address is 1, and what it's pointing to is just a tiny house. But then you go to house. It's the same size mailbox. The city gives them out. They're all generic mailboxes. But what mailbox 3 points to is an unsigned long, or a giant mansion of a house. Okay, it's a bigger data type. So all the mailboxes at the end of the street are all the same. When they go to deliver the mail or whatever, they all hold an address. It could be house 1, house 2, house 3, house 4. But then at the end of the driveway where the house sits, the house can be a different size. So the size of what the pointers contain are all the same because they only contain that address variable, right? And the address variable is always a hexadecimal variable of 8 digits. Okay, so it can point to a very simple or a very complex structure. Does that make sense? I don't want to move on before I know that you understand this, because you have to understand this. Okay, no worries. Okay, so you got it. Okay. What do you mean, can we use a reference for a pointer? There wouldn't be any point, haha, pun intended, to using a reference on a pointer because a pointer already points to an address. So if the pointer is pointing to an address and you already have access to that address, then modifying the address again itself wouldn't work. And I don't know if the compiler actually would. To be honest, I'm not sure, but there isn't any logic to actually needing, like you would never need to have a reference to a pointer, right? And I actually I don't know if you could because pointers can change and references can't. So if you set the reference to something that can change, it's not going to like that because references probably that anyways. Okay, so now let's look at storing an address in a pointer variable. Okay, so the compiler will make sure that the address is stored in a pointer variable of the correct type. Okay, so you will get compiler errors if you use the wrong type. So remember when we declared our pointers, okay, and here we have an int score 10, we initialized to 10, and a double high temp of 100.7. Okay, so this is just normal variables. We're used to working with those. Now down here, we're declaring a pointer. There's our key asterisks for declaring a pointer. Int score pointer. Okay, it's of type int, and we've initialized it to null pointer, so it's pointing to address 0 in memory. So there's no address. It's a house with it's a mailbox, sorry, with no number on it. It's a mailbox that's pointing to no house. It's not pointing to any driveway. Okay, now here we set score pointer to the reference of score. Okay, now because pointers contain addresses to variables, they point to a type of variable, we have to use the address operator on our variable score to point to the hexadecimal address in memory of what score or where score is pointing to that value. So here score pointer set to reference of scores is okay. But if we try to do score pointer set to the reference of high temp, well then that's going to give us a compiler error because you can't put a double, you can't have an int pointer point to a double, right? So it has to be the same type. Okay, here's another example. I think I just have the same slide twice. Whoops. So, okay, an important note, even though both these references, so reference of score and reference of high temp, are the same size of 4, okay, they won't be able to use a pointer for its address because it's for an int address, not for a double address, okay? Okay, so storing an address in a pointer variable. So to store an address in a pointer variable, we use the address operator. Pointers are variables, so they can change. Remember that? They can be null and they can be uninitialized. So that's super powerful because with references we can't change them, but with pointers we can. So here we declare two variables. We've got high temp and low temp, and we've initialized them to two different numbers. So we have a temp of 100.7 and a temp of 37.2. So our double with a pointer called temp pointer. So it's a pointer that points to a double. Now here we're setting our temp pointer equal to the reference of high temp. So this is going to point to the address of high temp. Then we set it to point to the address of low temp. And then we can set it to actually be null. So it's actually nice. You can actually change what your pointer points to depending on what you want to use it for. All right. So with that being said, let's go to an example in CodeLight. You can type some of this stuff out here from the PowerPoint. Follow along. We're going to go into the project called Simple Pointers. Where is it? Value of num. Okay, cool. So here we are. Yeah, simple pointers. Okay. So here we are including IOStream, vector, and string, and we're using namespace of std. Nothing new there. Okay. So the first thing is we're creating num, initialized to 10, and we print out the value of num. Then we print out the size of num, and then we're going to print out the address of num. And let's see what we get. So I actually get it on this side. Zoom in. So obviously we know the value, of num is 10. We know that the size of num is 4 on my machine. On yours, it might be 8. And then the address is a hexadecimal address that points to where the address in memory is actually storing this variable. Okay? Oh, cool. So now we want to make a pointer. So let's uncomment this. All right? Follow along if you want in your IDE. You can type this stuff out. So here we've made a pointer called p, and we're pointing to an int. All right? The value of p is going to be garbage because it's uninitialized. So it's going to be pointing to something random that I don't know in memory. Then we're going to print the address of p, so where it actually exists. And then we're going to print the size of p. Okay, so let's try that. Let's see what we've got. All right, so take a look here. Now, this is important to note. The value of p, so what the pointer points to, is this address. Where the pointer actually lives or exists is this address. Okay, and then the size is 8. So my pointer is actually 8. On your machine, it might only be 4. Okay, but it's 8, so it can contain up to 8 bytes. Okay, so now initializer print out the value of p again. So where it actually points to. Oh, look at that. It's a new garbage value. It was different last time. The address, okay, is different. And then size is 8, but now it's 0. We did null pointer, and now it's pointing to address 0. So it has nothing that it's pointing to. Cool. Okay, so coming down. Next example. So we've made an int pointer called p1, and we've initialized it to null. And we've made a double pointer called p2, and we've initialized it to 0 as well. We've also made a pointer of long, and a vector string pointer p4. We've also made a string p5. So this is the example that you were saying they would all be different. Now, what I want to try to annotate here for you guys with pointers, okay, as I draw with my pen, okay, is imagine, okay, you've probably all seen those post boxes, okay, at the edge of the street. This is my crude drawing of one. And some people who don't have mailboxes, they have a post box. And it serves an entire neighborhood. Okay, so, whoops. So, you have post boxes, and sometimes teenagers, they kick these over, right? All the high school kids, they walk up, they kick them over. Well, when you go to collect your mail, there's post box 1, there's post box 2, there's post box 3, there's post box 4, and so on, right? 5, 6, 7, 8, 9, 10, 11. Okay, so we've got a post box. Now, they're all the same size, okay? Now, this post box is at address, I don't know, let's say 100 Bay Street. This is where the post box is in literal physical address. Now, it has an address here of 1 at 100 Bay, so it'd be a 100, and then that's the address of the pointer. But the value of the pointer points to house 1, which could be just this little cute shack at 200 Bay Street. Okay? And then imagine this house, postbox 2, it points to some bigger mansion, decent sized home of, this is 300 Bay Street. I don't know. hoping this analogy is making sense. So these are all the same. They can hold a number up to however many digits, and they're all the same size. So this is our pointer, okay? And our pointer can hold a pointer that points to something small like an int, okay? But also it can point to something large like a vector. And the address of the pointer may be like this, 101, okay, or 102. But the points to can be big or small, okay? So you can point to an int, a small data structure, or can point to a vector, a large data structure. But the size of a pointer is all the same. And then the address of a pointer versus the value of what the pointer points to are different. And we'll get into that a little bit more, but hopefully that analogy helped as we go through this example. So let's take a look. We're going to print out, I'm going to comment this out. And we're going to print out, I've got 5 pointers here. 1 points to an int, 1 points to a double, 1 points to a long, 1 points to a vector, and 1 points to, and 1 points to a string. I just ran it and then it closed again. And then I print the size of each one, and look at that. They're all 8 because they all contain 8 bytes of being able to point to an address. Very good. Okay, so moving on. Down here, here's another example. So here, I've got 2 variables, score and high temp, and then I make a score pointer that points to an int, and I initialize it to null, or address 0. Then I set my score pointer to the address of score, okay? And if we want to see what the address of score is, well, I've printed it out here. So first I print the value, which should be 10. This should print 10, okay? Then this should print the address of where variable score lives. So some hexadecimal address. I don't know, something like that. I just made that up. It'll print the address. And then the value of the score pointer, well, let's look at what that looks like here. Let's see. When you actually print a Okay, so we got 10. We expected that. Then we get the address of score. I was actually pretty close with my guess. And then the value of score pointer is the exact same. So that's important to notice. The value of what pointer holds is it points to the address of what it was set to. Okay? Not the value of what it's set to, but the address of what it's pointing to. Now, if I tried to do this and I set it to a double, we'll get a compiler error. Whoops. We'll get a compiler error down here because I'm trying to set it to a double. As you can see, cannot convert double to int, double pointer to int pointer. So we have to leave that commented out. Very good. All right, cool. So we took a short little break there, but now we are going to get into dereferencing a pointer. And that may sound a little scary, but honestly, all it is accessing the data that we're pointing to. Okay, so far we've learned how to declare a pointer and set it, but we don't know how to read it. So we want to actually be able to access what we're pointing to. So in this example, okay, we use the asterisk to declare a pointer in that second line of code. So we have score set to initialized 100, and we have initialized our score pointer to the reference of score, so the address that score is located at. And so now score pointer is pointing to an int, which is going to hold the address of this variable. Okay, so to get the actual data at the address contained in the pointer, we have to use the dereferencing operator. Now, the dereferencing operator is the asterisk, and many people have criticized C++'s choice to use the asterisk as the dereference symbol, as well as the symbol when declaring a pointer, but it is what it is. And sometimes, You just have to remember, okay, if you use it the very first time, once you initialize it, that's how you declare it. And every time you use it after that, okay, so here we've got asterisk score pointer, then we're dereferencing it. We're reading from it. So here we've got the value, okay, but then we've got the dereference operator, which is actually going to get, we've got the address, we've got the dereference operator, which is going to give us the value at that address, which will print 100. Then here we've got the dereference operator again, and we've used an assignment. So we've assigned it to, if we dereference it again and read it to the console, it'll now be 200. And because a pointer points to the original variable, when we print score again, well, we've actually updated the original because it's a pointer, right? So this is pointing to the address, which holds this value. When we change what the address is pointing to's value to 200, then when we go back to printing the original value, which is at the same address, it's going to be updated to 200. So we can see that right here. Okay. So after we use the first asterisk to declare the pointer, then every time after that, the asterisk is used to dereference it. Okay, good. So to access the data we're pointing to, here's another example where we've made two doubles, high temp and low temp. Okay, and then we've made a double pointer, which is pointing to the address of high temp. Now, when we see out to the console and dereference temp pointer, it'll print out 100.7 because it's pointing to this. And then we're dereferencing it, which means we're going to get what it's pointing to's value. Okay, then we set temp pointer and update it to the reference of low temp. And then when we print out temp pointer again, now we're going to get the value of what low temp points to. So setting a pointer and then changing its value and what it points to is actually very powerful. And we'll see how and why later. But it's very important to know that that's one of the main advantages to pointers over references. References we can't change. Okay, so accessing the data we're pointing to now with some strings. So we've got a string named Frank, and then we've got a pointer that points to a string, and it's set or initialized to the value of the name reference to name. So it's going to be pointing to the same address table, and it will print out Frank. Now, if we set name equal to James, okay, the actual value, the variable this time, instead of setting the dereferenced pointer to the value and then printing out the variable, now we're setting the variable to this, and when we dereference the pointer also gets updated. So they're the same object, if you think about it like this. There's the pointer, and then there's the variable, okay? If we update the variable, okay, then we update the pointer. If we update the pointer, then we update the variable. And they're pointing to the same address in memory, okay? The variable and the pointer point to the same hexadecimal address, and if we update whatever value is stored at that hexadecimal address and we access it via the pointer or via the variable, we get the same result. Okay, so it doesn't matter which way you do it. So let's go to CodeLite. I've got a little project called Dereferencing here, and we're going to, look at some of this stuff in action. So I'll comment out the code from before, and if you want to follow along, some of the code is in the PowerPoint there, and you can just type it out, or you can follow along in the video here. So let's take a look at this. We've got two variables, and one is an int that's initialized to 100, and one is a pointer that points to an int that is initialized to the reference of score. Okay, so now what we want to do is print out the value of that pointer, and we're going to do that by using the dereference key symbol of the asterisk in front of our pointer, which will print out 100. Okay, now, same example as basically what we looked at on the PowerPoint. So now what we want to do is use the dereference operator on our pointer and set it or assign it to a new value of 200. Then when we print out the dereferenced pointer, we get 200, and then when we print the original score, we should also get 200. So let's run this and let's see if that's true, which it will be because tested it and that's what it's supposed to do. So here is 100, okay, from our first print statement of the pointer. So that's dereferenced. That's getting the value at the memory address. Then we've updated the value at the memory address and printed the value at the memory address again. And then we've just printed the variable itself. Very good. Okay, cool. So now I'll comment that out again, and we'll move on to the next section. So here we've got the same thing from the slides, same example. High temp, low temp, both doubles. One's 100, one's 37. And then we've got a pointer that points to a double, and we've initialized it to point to high temp, so the address in memory of high temp. And then we print out the dereferenced pointer, which will get the address in memory's value of 100.7. So it'll print out 107. And then we update the pointer to our low temp reference. And then we print out the dereferenced pointer again, and it should print out 37.4. So run it. There it is. So you can change what the pointer points to. Very good. Now, last example, which we looked at with string. Except this one, we're also going to look at some dynamic loops. So we've got a string named Frank, and we've got a pointer, string pointer, that points to a string, and we've initialized it to the name Frank. So when we print out the dereferenced string pointer, it should print out Frank, and then when we update our original variable name to James, then when we print out the dereferenced pointer again, since it's pointing to the same address in memory, it should also be James. And the second one we get is James. Okay, so that works. Next, okay, we've got a vector of strings, named it Stooges, and got Larry, Moe, and Curly. Then we've made a vector pointer that points to a vector of strings that's initialized to nothing or 0. Okay, so no address. Then we make a vector pointer we assign it to the address of Stooges. So instead of copying the vector, we set it to the actual original object of Stooges right here. So we've got our pointer, which is set to a vector of strings, and we have set it to our reference to Stooges. Now, we want to actually print out a stooge. Okay, so we want to print out Larry. And this is where, we'll get into using subscript notation, but for now we'll use vector notation. We can actually access vectors through our pointer that points to vectors. And I know this is going to get really wordy and sound confusing, but we've got a pointer that points to vectors, and we're going to access the original vector element. So we've printed out a string here and concatenated it. And then here we have our dereferenced pointer. Okay, so this name could be whatever you want to call it, but here's our pointer that points to the vector's address, and we've dereferenced it. And then we do the dot at, and then whatever element we want. Now we have to put the dereferenced vector in brackets because this dot here actually has a higher precedence order than the dereference operator of the asterisk. So because we want to dereference it first before we access the element, we have to put it in brackets so it's dereferenced first. So what happens? Well, it'll print out the first stooge, Larry, okay? Because we used at 0. So there's the ranged base for loop. We see out stooges, and then we go for each stooge, auto stooge in the vector that we've dereferenced. Okay, right here, we've dereferenced it with the asterisk symbol. For each stooge in stooges, which is basically what this is because it's not the address in memory, it's now the value that the address in memory points to. So basically it's saying for each stooge in stooges, see out the stooge. And there we are. We get Larry, Moe, Curly. Cool. So that is how that works. Hopefully that makes sense. The next section I want to cover with you guys is dynamic memory allocation, or allocating storage from the heap at runtime, okay? So we've talked about pointers, we've talked about how to create them, we've talked about how to access them and read from them. Now we want to talk about actually using dynamic memory allocation, okay? So we often don't know how much storage we need until we need it. So during runtime. So we can actually allocate this storage for a variable during our program's runtime. So imagine if you're making an operating system or something like that, or a driver, and you don't know how many users you'll have logging in or something like that. you need to allocate and store it dynamically, which is why C++ is really great for doing this with pointers. So we can, you know, recall back to when we talked about arrays in C++. We had to explicitly provide the size of what the array was, and it was fixed to that size. You couldn't change it. But vectors, they grow and they shrink dynamically, right? They update automatically by using the pushback function. So we can actually use pointers to access our newly allocated heap storage, okay, when we make dynamic memory in the heap. From the heap, that is kind of how vectors work. But what if we need to do this with objects, right? Not vectors. Well, that's where this dynamic memory allocation comes in. And all of that memory is allocated via a pointer, okay, from the heap or the free store, right? Okay. Again, like I said earlier, we'll use dynamic memory allocation later on when we talk about object-oriented programming. But for now, we have to understand dynamic memory allocation first. So let's see, how do we allocate storage at runtime? Well, we use the new keyword here in bold, okay? So we have to declare our int pointer to point to an integer, obviously, that's the first line. So we've got an int underscore pointer that points to an integer, and we've initialized it to nothing. And then to actually allocate memory on the heap, then we take our pointer and we set it to new int, which will allocate an integer on the heap. Rather than assigning the address of some integer variable, okay, as what we've previously done, why don't we create an integer at runtime that's on the heap, okay? So what we've done in the past examples, okay, and you'll see me do this little annotation multiple times today, but when you Google dynamic memory allocation, you'll see this similar type of thing. We've got, runtime. We've got our variables down here, int pointer, right? Int underscore pointer. And then what we've done in the past is we've set it to something, some local variable somewhere else, like instead. Now, what we're doing here is we're actually creating, with the new keyword, we're actually creating something on the heap, which is a different block of memory. This is the heap here. Try my best to write it. And here we're creating a new int. So this is actually going to be an integer up here. Instead of copying the value from an existing int of num, we're actually creating a new int up here on the heap, which will live up here. Okay? And the stack, the stack disappears when the local variables or the functions that are called, end. But the heap is always, it's in memory. And the pointer is the only way we have to actually access this. This doesn't have a variable name like what we're used to. So the only way to access it is the pointer, the address in memory on the heap. Okay, so pretty cool, right? This is what's on the free store, and this is how the variables are addressed in the int pointer. Okay, so pretty easy to declare. We just use the new keyword. This allocates storage for an integer on the heap, and it stores its address in int pointer. So this is the heap. This is where it is actually stored, but then the address to it is stored in our pointer object. So now we can use that pointer to access the integer we just created. So this first cout statement right here, we're printing out the pointer, okay? What is going to happen is this is going to be the first output statement that displays the value of the int pointer. So this is simply the address of the newly created integer. Okay, if we want to get to that integer, we need to dereference the pointer. So this is just the value of the newly the address of the newly created integer. So this is the address of memory on the heap. Okay, so this is up here. Now, the second cout statement, okay, we're using, notice, the dereference operator, the asterisk. And notice we get a really large number here. Well, this is garbage, okay? This is actually just garbage data, and that's because the integer wasn't initialized. So it's just garbage data. This is the actual value. So here we've got the address. This is the actual value of what that address contains. And because it wasn't initialized, it's just garbage data right now, okay? So in order to actually assign a value to that integer on the heap, we have to dereference the pointer. So same way that we just accessed it, well, we have to assign it the same way using the operator, and then assign it to a value of 100, okay, and store it. So now if we print it out, then what's happening is it's going to print out 100, which we just assigned to it, and that's on the heap. Important to note, okay, in this scenario, when you allocate storage in this way with dynamic memory allocation, the storage is on the heap. The allocated storage will contain garbage data until you initialize it. Okay, the allocated storage does not have a name like our normal, variable with the word num. It doesn't have a name, so the only way we can get to that storage is via this pointer address right here. Okay? If we lose this pointer because it goes out of scope, or we reassign it, or say we set it to null pointer for some reason, accidentally or something, then you've lost your only way, okay? That's my giant X. Connect address in memory. And then that's how you get a memory leak, okay? Because this exists, but you have no way to access it or delete it or anything like that. So that's how you get a memory leak. So finally, when you're done using the storage on the heap, you have to do something that's called deallocating the storage. So it's again available to the rest of the program. Okay, so how do we do that? Well, let's take a look on the next slide here. So dynamic memory allocation, deallocating the storage that we just allocated, we have to use the delete keyword. So we do the same as the last slide, okay? We created an int pointer that points to an int, initialized it to null, set a new int on the heap, okay? Whatever, we do all the same stuff. We do whatever we're doing with the pointer. And then once we're done with it, we just use the delete keyword and then put our pointer's name. And that frees the allocated storage from the heap. So we can use the pointer as we wish, and then when we're done with it, we just have to release it. Okay, release and deallocate are the same words, so you'll hear me use them interchangeably throughout this. All right, so here, what we're doing is we're allocating an entire array of integers on the heap at runtime. So I've created a pointer that is pointing to an int, all right? It's called array pointer, but it's pointing to an int, and it's initialized to null. I've also created a variable called size, and it's initialized to nothing as well. Now I ask the user how big do they want the array, and then I save their variable into size, and then I create my array pointer equals new int, and I allocate an array on the heap, an int array, in square brackets here, passing the size variable. Okay, so if the user put in 5, this would create 5 ints, an array of 5 ints. So we can access the. I know this might be a little bit confusing, but we use the new keyword operator, and then this will allocate that many integers on the heap contiguously meaning one block altogether in memory. And if it's successful, then the address of the first integer is stored in array underscore pointer. All right. And after we're done with the memory, we have to obviously release or deallocate it. Now, if you'll remember with arrays, the way that they work is their memory addresses, right? And the oh, my screen went a little bit funky when I wanted to annotate here. The first item in array, if you have an array of nums, right? And say we have 3 elements in it. We have 1, 2, and 3. Well, the way that it actually works is if we were to print just nums itself, just the word with no element index, well, then we would get the memory address of the first element in the array, which would be some hexadecimal address like that. And then the second element, if it's an int and the ints on my machine are 4 bytes, okay, it's going to take that hex address, and then it's just going to add +4 to the end. So then this would be 0x f f d instead of 4. Now it would be 8, and that is now my. That's the way arrays work, remember? That's the same way pointers work. So there's kind of a relationship there between pointers and arrays, and we'll talk about that in a little bit. But here, to delete the array pointer, so we ask the user how many we want to create. They put in 5. We just delete, and then we delete the array pointer. But remember, now, because we've created like 5 of them, we have to put in square brackets between the delete and the name of the pointer, and they have to be empty, and that will free all the allocated storage there because we created more than one, right? So this last statement is what deallocates the memory for an array. Okay, good. Let's go to code light, and here you'll see another little diagram of, you've got your stack, and you've got your global code for your global variables. Your local variables live in the stack, and then we've got the heap storage up here. So let's do some dynamic memory allocation in the dynamic memory project. All right. So I'll comment this stuff out. So coming down to dynamic memory. Okay. Let's do this. So I'm going to walk through it a little bit slowly, and then at first, and then we'll kind of move through this. But I've created a pointer. It's the same as on the slides. And then here we're doing the actual dynamic memory allocation using that new keyword, and it's going to create an integer on the heap. What's going to happen is that storage for the integer is going to be stored. Whoops. I want to see what the rest of this stored. The address will be stored in the int pointer. Okay, because I set int pointer equal to new int. So this is going to hold the address that points to the. When I see out the dereferenced pointer, okay, to actually get the value, it would just be garbage. But since I'm only outing the pointer itself, this will just display the hex address or memory location where that integer is on the heap. Okay, and then here I just delete it and I release that memory. Okay, so that's what will happen here. So let's run this. Comment this out too. Okay, so we've created our pointer. We created a new integer on the heap. I've still got the program running. Bring this over. Okay, so we can see what's happening here. Well, it only printed one line from line 102, and it's printing out that address in memory of the new integer. So this is where that new integer in hexadecimal, that's where it lives on the heap, okay, in dynamic memory. Now, here what I'm doing is I'm asking the user, how many temps would you like? All right, so how many temperatures would you like to enter? So what I've done is I've created a size variable using the size_t keyword and initialize it to 0. And what we want to do is create a whole contiguous block of memory on the heap. So we want to create a bunch of doubles. Contiguous means all concurrent, basically. They're all beside each other. It's a big block of memory. And we don't know how many temperatures we want to enter, right? So we're going to ask the user and store it in a size variable. And then what we're also doing is we're creating a pointer that points to doubles, okay, and initializing it to null. When we ask the user how many temps, we store it in the size variable. And then this is where we put size in square brackets. Comment. So I set my double pointer equal to a new contiguous block of memory on the heap. All right. I'm going to create a double, but I'm going to pass, it's going to be an array of doubles because I'm using square brackets now, and the size of whatever number I enter. So if I enter 5, it'll be 5 doubles. Then when I print out temp pointer, this will print out the address of that heap address, okay, for the first array, the first element in the array. Now there'll be a way for me, I'll show you later how to print through an array and loop through it, but for now we're just going to print the address of the array that we created, and then here we just delete it. Okay, so let's run this. I didn't have some of that code uncommented, so I have to rerun the program. But here, when I run it and I ask the user how many temps, let's say I want to create 10 doubles. Well, there's the address of, is that right? That should be right. Oh, I was confused there for a second. I thought the address for my int pointer and the for my new int that I created on the heap and the address for my double that I created on the heap array was the same, but there's actually a difference here between 1 and 8. Okay, and then both of those were released or deallocated because we used the delete keyword there. So there's no memory leak. Okay, so that's how you do that. Cool. All right, so basically what we did there was we created an int, okay, down here. And you'll see that int was created up on the heap in the free store. And we created a pointer that points to the address on the heap. And down here, we have a pointer for doubles and that of doubles. So this is an array. It's much longer up on the heap. Cool. All right. And then for this example, if we wanted to create a leak in your, if you wanted to create a memory leak and I didn't do the delete temp pointer in that last, if I didn't do this line of code and I didn't release it, but instead I set my temp pointer to a new address. So remember my temp pointer here, when I print this out, that was that hex address of the first element in the array in the heap. Okay. If I now set my temp pointer, to a new address or say to null, then what happens is I lose that connection or that pointer to the address in the heap. And I don't know where that address in the heap is, right? If I don't remember where it was, if I don't write it down or something like that, it's gone. And then we have a memory leak because there's no way to access that data anymore. There's no variable name. It's just an address, okay, that's in your dynamic memory. And if you get rid of that connection between the pointer and the address in the heap, you're kind of screwed and you have a memory leak. So just keep that in mind. That's how you get a memory leak. Another way to get a memory leak is if you were to continue to create doubles. So here, this is the code that we created, new double on the heap in the free store with the new keyword, and we pass in the size variable, but we put it in a loop, and we basically put it in a forever loop, which is while true. Then you'll get something here called bad alloc, which is bad allocate. To create another double, because what's actually going to happen is it won't be able to use the new keyword because the heap is full after throwing an instance of standard bad alloc. All right, so that's what a memory leak looks like. Okay, so let's talk a little bit about the relationship between arrays and pointers. So I kind of talked about it a bit before, how an array holds the name of the first address in the first element of the array, and the value of a pointer variable is also an address. So if a pointer points to the same data type as the array element, then the pointer and the array name can be used interchangeably. Almost. Okay, so it's a good question, and it's critical that you understand the relationship between arrays and pointers, because if a pointer points to the same data as the array, then the pointer and the array name are the same as far as C++ is concerned. The only difference is that the array name is not a variable, so you can't change it. Otherwise, all the calculations done to access array elements can be done with the array name or with the pointer name, okay? So here I've got an array of scores that's of type integer, and I've got 3 values in it, 100, 95, 89. And if I print out the name scores, I get the address of the first element in my array. Okay, now if I print out pointer of scores, right, if I've dereferenced it, I get the first element. Now, if I create a pointer, okay, so this is just using the dereference, whoops, I'm going to slide ahead, the dereference operator. Now, if I create a pointer of type int and I set it to scores, an address, now I don't have to use the reference character of % here, right? It's address operator because I don't need it. It's already an address. So I set my pointer to point to that address, and if I print out my pointer, I'm going to get the same address as when I print out my array. And if I dereference my pointer, just like I dereferenced my array here, I get the same thing. I get the first element in the array. So you might think, oh, wait, I can't dereference an array. I can't dereference scores here because it's an array. I can't dereference arrays. But you can, because arrays store points to the memory location for the address. So it's the same for pointers. Pretty cool. All right, so here again, I've got the same array, and I've got a pointer, and I point it to the array. Okay, and then when I print out my array at 0, 1, and 2, I get 195 and 89. So if we can pretty much use an array name and a pointer name interchangeably, that means we should be able to use array subscripting on a pointer, right? What do you guys think? Do you think that that's correct? If I can use array notation or subscript notation on arrays, and array names and pointer names are interchangeable, then I should be able to use subscripting notation on pointers. What do you guys think? In chat, what do you guys think? Is it starting to get confusing for you, Simon? He says, I think that that's enough for today. It's not too confusing. Just think about it. I think yes. So here we've got an array. Here we've got our pointer that points to the array. When we print out the array, we get the address, okay? And then when we print out the array plus 1, right, we use offset notation here. Then we get the same memory address plus, remember, it's 4 bytes, so we go to the next element in the array, 4 bytes, and if we do plus 2, we go 4 and 4, which is 8, so now we go plus 8. So yes, you can use either notation on arrays or pointers because they're the same. So look at this. Subscript and offset notation are equivalent for arrays and for pointers. So here's my array of 1, 2, 3, 4, 5. Here's my pointer that points to that array of 1, 2, 3, 4, 5. If I do array name with subscript notation or pointer name with subscript notation, it's the same as doing array name with my offset plus 1 or plus 1, but I have the dereference variable on the outside. Right? Pretty simple. So let's go to CodeLite and I'll show you what that looks like in some code here with arrays and pointers. Okay, this is the last example here in code. So I've got my array, okay, and I've got an array of scores of 195 and 89, and my value of scores is going to be the actual memory address. So if I print this out, oops, I should probably comment this thing out. Okay, let's do this. I actually run my program. Okay, so if I print out just the array name itself, I get the address, okay, for here. Now, if I create a pointer that points to an int that is now pointing to my print name address in memory, they're the same. Okay, good. Now I printed a bunch of lines here, and then I do subscript notation on my array, 0, 1, 2. So I should get the values 195, 89, and I do. And then I use my pointer and I do the same notation, 0, 1, 2, and look, I get the same thing. And we'll see that it's actually identical for all options. If we do offset notation, so we use the dereference operator, and then we do +1, +2 to get to the different elements, indexes in the element, or we can do that in our array as well. So we can do it either or, pointer or array, it's equivalent. Hopefully that makes sense. Hopefully that's not too confusing. I'll end this recording here for a little bit, and we'll just take a sec to answer some questions and clear anything that might be confusing about pointers. And the next little section will be about using arithmetic on pointers. So I'll just end this recording here because it's getting pretty long, and break it up a little bit into another section.